Hello, we're going to be looking at Chapter 6, which is time varying signals, and the only difference between this chapter and prior chapters is now we're varying the waveform of the DC signal, but it's not DC anymore, it's time varying. So basically it's at a point in time. We can use the same calculations that we did before, but it's going to the same problem is going to have to be calculated multiple times. And we'll find that through the course of this chapter. At the end of this chapter, we're going to talk about sine wave signals, which are a little bit different, but they're basically just time varying signals that have a value that we're just going to capture their RMS value. So again, it's the same as we've done before for the most part in this chapter, but with time varying signals. So we define as a second an average solar day divided by 86,400. I think everybody knows what a second is. It's that little piece of time that we consider about the time of a heartbeat. In electrical work, we always start at some point, and we always refer to that as t equals 0. So it's our starting point. It's ready, set, go. It's the time that we pick that is our reference. So we can reference sometime after t equals 0 or sometime before t equals 0. And this shows that. Here would be t equals 0. Here would be 1 second prior. Here would be 2 seconds prior, 3 seconds prior. And here would be after t equals 0. So as time marches on, we're going to the right. So again, we can look at a problem and we can say we have a waveform, and we can say, okay, at that certain point in time, t equals something. What does V equal? Or what does, after we close the switch, what happens to that signal? And in this case, this is a ramp form, and we can look at it and we can see right here it is. So at t equals 0, we start, and then each time we click off 1 more second, we go up another 5 volts. But here we are, 1 second, 5 volts, 2 seconds, 10 volts, 3 seconds, 15 volts, etc., etc., etc. This is a triangular waveform which has a peak of 2 amps. This is a current waveform, 2 amps at 1 second, then it drops down to minus 2 amps at 3 seconds, and it goes back and forth and just repeats. Here are some graphs of what we would have to, and what we would have to do would be to calculate the value at each of these points, and then find the value that we would be looking for, and then we would graph that point as well. So basically all of our answers are graphs at various values. Okay, so here we have a problem we talk about in the following example. We close the switch at t equals 0. Before t equals 0, the voltage across the 5 k ohm is 0. After the switch closes, we have a current that flows through it, but the full 10 volts flows through it, so we have a current through it of 10 milliamps. So if we're asked to graph the value of current up until t equals 0, it's 0. It's 0. We're coming along here at 0, and then all of a sudden, and when we close the switch, it's a square wave, isn't it? It jumps immediately up to 10 milliamps, and it's fully a square wave at that point. But it stays at 10 amps until we do something else, until we either turn off the power supply or we add another resistor or something like that. But you can plot these points all the way across if you want to. Here is another point. This is another question. And in this question, we selectively close these switches. So basically, at t equals 0, none of the switches are closed. At t equals 0, this switch closes. Well, you can see if that happens, we're still just going through this resistor. Simple circuit, 9 volts, 6 k ohms. You can calculate the current through that. Then at a later time, we close the B switch as well. Now, if we had the A switch open and the B switch closed, it wouldn't make any difference. But with the A switch closed and now the B switch closed, the resistance drops. These two resistors are in parallel. So now we're going to go with 6 and a 6 in parallel, and that's a 3. So now we've got 3 K and then 9 volts. So we've got a higher current. And at a later time, A and B are now closed, C closes. So now we've got another lower voltage of resistance because the 3 are in parallel. So we drop to 2K, and then we've got 9 divided by 2K, or 4.5 milliamps. So now we can graph this. We can actually graph the current at each of these steps. Here it is with the first 6K, then the two 6K in parallel, and then the three 6K in parallel. So you graph it at each step. So it's a three-step problem. You have to figure out the problem 3 times. Instead of just once, you have to do it 3 times. Other than that, it's the same problem. Here is a time-varying signal. It's the symbol for a time-varying signal. And here is that signal. This is a ramp form. So now what we're trying to do is we're going to traffic graph the current through the 10K resistor. Now notice that the waveform of the output looks the same style as the wave output of the input. So you basically, if you have a ramp for your input, you're going to have a ramp for your output. If you have a triangular waveform, triangular waveform. If you have a sine, you have a sine, etc., etc., etc. And what do? You take a point and you calculate the point on the other graph. Now, and sometimes you can use the same graph, but many times you can't. Here's another point. There it is. Here's another point. There it is. Draw a straight line through them, and you got the answer. That's your answer. Okay, so figure 6.7 describes A describes a non-varying waveform for current. B describes a sine waveform for current. The sine wave is also used to describe alternating current or voltage. We'll be given more information at a later time about AC current. Other than that, basically it's good enough to say that it wiggles. So this is shows a wave or a voltage source with a time varying signal. Now the only basic thing we do is we drop the uppercase. We used to say I equals V over R. Now we say lowercase little I equals little v over R, but everything else is the same. Everything remains the same, except for power, and that we'll talk about later. Okay. So basically, this is the same problem as it was before. You just have to recalculate it for more than one time. So if I say my voltage supply was, say for instance, 6 volts, so over here 6 volts, then I could calculate my current for 6 volts. Then I could calculate it for 12. Then I could calculate it for 18, and then graph those results and have my answer. So I have to calculate it more than once. So basically what you do is, in this case, what you have to do is you have to redraw the supply with the V Thevenin supply and the new R Thevenin as well. And now you've come up with a new set of currents. Okay. So that is our plan. And we will follow that through the rest of this chapter. So we notice that V Thevenin is, when V Thevenin is 2 volts, 2K and 2K are in series, so that's 2 divided by 4, or 0.5 milliamp. At V equals 4, we have 4 divided by 4K, or 1 milliamp. At T equals 3, V Thevenin is 6, or 6 divided by 4K is 1.5 milliamp. We can see by observation that a ramp input yields a ramp output. What a concept. Okay, so basically we're using the same rules that we had from before. Here we have a triangular waveform, and we find our R Thevenin, and we look at V. Now, in triangular waveforms, all you have to do is at 0, it's going to be 0. Your output's going to be 0. But at the peak value, that's all you need to do is you need to calculate the peak. So I need to calculate this as if V equals 10 volts. I put V equals 10 volts in here, and I calculate my peak. So V Thevenin is 5, and then that would be my peak. And then I calculate my I based on that. So my I is V is 10 volts, or excuse me, 5 volts divided by 5 plus 10K, or 0.333 milliamps. And we calculate it, and we can go at 5 at t equals 1. You can also draw it at t equals 2, t equals 3, and away you go. Here is a square wave. So again, calculate the value at the peak at 1 milliamp, and then use that to calculate your voltage. So basically, the output's going to look like the input, so this is going to be a square wave. So I'm going to go 1 milliamp through 20K. It's going to be 20 volts. It's going to jump to minus 20 volts and back and forth. It's going to look like the same kind of square wave that we had before. So we've got an idea now that we can basically use the same problems that we've had before, and now we're just adding a little bit of spice to them. So we're doing the same thing we've always done. So here we do what? We pick the peak. We pick the 10 volts, and we now say, what is the current? Well, it's 10 divided by 2K, or 5 milliamps. For the sawtooth, we pick the 50 volts, and we calculate the current based on the 50, and we say, okay, I've got 5 milliamps at the peak, and I've got through V1 I've got 8K, so I've got 40 volts, and through the V2 for the 2K I've got 20 volt, or I've got 10 volts. So I basically, and these two had better add up to that, and they do. Alright, so this one right here, we are feeding 9 volts into this circuit, and we want to know what? We want to find the value of the currents I1, I2, and I3, and I4 and I5. So let's just look and see what we got. So at t equals 1 millisecond, 2 milliseconds, 3 milliseconds, we find the value at 9. And the I1, the I2, and the I3 are calculated right here for 9 volts. So this is a solve the whole thing problem. This is a crunch problem. Got all those values, and there they are. And now the output is going to look like the input, but with just those peak values at each one of those cases. So if you calculate your values where you've got your peak, all these are your peak values as well. Now, looking at the sine wave is the wave generated by the power company and is what is expected when we plug a device into a household outlet. We will discuss such quantities as the period and frequency as well as the amplitude of a sine wave. And you can spell it either S-I-N or S-I-N-E, it doesn't matter. Usually, as we're officially talking about it, we say S-I-N-E, but when we're abbreviating it, we'll say sine, S-I-N. It's always called sine wave. Okay, so we are now looking at a sine wave and how an AC generator generates that. And you can look at it and you can see that it actually is generated by the forces, the magnetic forces that are generated on a by having a magnetic field spinning. And as they go higher, as the magnetic field gets closer to the coils, they get higher. The value of the voltage and the current goes higher, and as it spins away from it, it goes lower. And then when you go negative, it goes further negative. So it's got a 0 point, it's got a peak, it's got another 0 point, and it's got a negative peak. So the generator and the motor work the same way, and they basically complement each other. One does the generating of the power, one does the generating of the electricity. Anyway, so the period is the time between, as I explained it, when it does it to when it does it again. So here it starts up, and here it starts down, but that's going in the wrong direction, so it's not a period from there, but the period is from this point to this point. So when it cuts the zero axis, to when it cuts the zero axis going in the same direction again is the period. So the period of this waveform is 4 milliseconds. So the period is, it's called capital T, and it's 4 milliseconds. So when it does it to when it does it again, as I sometimes say, repeat and repeat, and then we get the idea. But anyway, that's what it, when it does it to when it does it again. So the capital T is called the period. So here we have it. Pete and repeat were in a boat. Pete fell out. Who was left? Here's Pete, and here he is again. Here's Pete, and here's repeat, and here's repeat, and here's repeat, and here's repeat, and here's repeat. So basically, this is a higher frequency signal than this one right up here. The frequency is defined as the number of cycles divided by the period of those cycles. But if it's one cycle, it would just be 1 divided by t. So usually the frequency is 1 divided by the period of one cycle. Again, if we only use one cycle, F is 1 over t. So here is the period of this waveform. T is the period of the waveform. And if you ask, okay, here's 0.2 seconds, that would be the period. What would be its frequency? 1 divided by 0.2, or 5 hertz. This would be the 5 hertz signal. 4 milliseconds would be 1 divided by 0.004, or what? 250, right? That would be 250 hertz. Okay. So, if we have a sine wave, if we have the instantaneous value of R, we have the instantaneous value of I, because R is the same. So if we have a peak value, let's say we have a peak value of 5, or we had a peak value of 20 millivolts or whatever, that would be the same. We would calculate everything based on that. So our instantaneous value, if we have this as our input signal, we would use the instantaneous value of the peak, and that would be the value we would use at this point. So we'd say 9 volt right here. We do our calculations based on that 9 volts. And here we are again, those same values we had before. Nothing different about the instantaneous values. Now, one of the things you can do is with an oscilloscope is look at the waveforms, and this is how you would actually see a time-varying waveform. And this is in our lab today, and we're going to talk about this week in our lab about the oscilloscope. There is no lab to hand in, but it is something that you should try, is to use the oscilloscope to be able to figure out some of the knobs on how to use the oscilloscope to display your signal that you want to have displayed. That's what we're going to be doing, is displaying various time-varying signals on the oscilloscope in the next few weeks. So frequency has something to do as well with the pitch of an instrument. Okay. So if we talk about a frequency, we're also talking about that frequency at which certain sounds occur. If you're in the range of a microphone, if you have a certain waveform, that it would give you a certain pitch of that signal. Okay, so a high pitch is a high frequency, and a low pitch is a low frequency. And I want to remind you that the human ear cannot hear below about 20 hertz. And if you're ever in a danger zone where you can get hurt from very low frequency noise, please get out. If you feel uncomfortable but you can't hear the noise, there very well may be a huge, very, very low frequency noise that is being created, and it can definitely damage your ears. And I have a good friend that happened to, and I would not want that to happen to you. So basically, you can hear things from about 20 hertz or 15 hertz up to about 40 kilohertz. But here's some of those frequencies. You can hear 220 hertz. That's the note A, and A sharp would be 233. Now, it's interesting to note that the difference between one octave and one octave above the original octave is what? The frequency is doubled. So from 220 to 440, we go from A back to A, but at an octave higher than the original signal. And if you want to go to another one, you would go 880, but you would double it again. So basically, that would be your waveform would go from one signal to another. Now, like for a violin, does not look like a sine wave, or for a human voice does not look like a sine wave, but even then, it is a time-varying signal that it gives its various characteristics by you using but the frequency of the note would be changed by the number of times that it repeats per second, or the number of hertz. And this is the piano, and this would be the way that you would look at the keys on the piano, but from one octave to one octave above that. So here, from the note right here is here's your middle C, and one octave above it would be a C, one octave above middle C, and here would be the next octave above it, and here would be one octave below. But each time you go one octave up, you're doubling the frequency of the waveform. Okay. So there's various attributes to a sine wave. One is called the peak value. It would be from 0 to the top value. That would be called the peak. The peak to peak would be from the very tippy top part to the very bottom part. So that would be the peak to peak value. Now here is a waveform that would be looking at it at like an equivalency of a bandsaw and a jigsaw. Okay. So one is a continuous motion. Like this would be a DC. So you're cutting something continuously. You're rotating and cutting with the cutting blade continuously. This one goes up and down and up and down and up and down and up and down and up and down. That would be your AC. So this was a mechanical equivalent to AC and DC. Here we are having what? We've got so many times, so many cuts that we would have with a DC signal, which would be like the bandsaw, continuous, and here we would have with the cuts with the up and down. And there is an equivalent between the two. Well, we're going to discover what that is in a minute. So if I have a waveform, and the average value would be 0.637 times the peak. The peak to peak is 2 times the peak, but the RMS value is 0.707 times the peak. So the peak times 0.707 is the value of the root mean square. And why is that important? Well, the root mean square value is the same value that you would use to calculate power. So if I had 2 volts DC and I had 2 volts RMS AC, they would give me equivalent power if put through the same circuit. So RMS is a way of defining equivalency so that we can get AC to DC. Now, at 0.07 is a kind of an interesting number, because what is that? That's the square root of 2, isn't it? That's the square root of 2. So if you can remember the square root of 2, you can say the peak value divided by the square root of 2, or the peak value times 0.707, is the RMS value. So we have 110, right? That's what we have coming out of the wall. Okay, so that divided by 0.707 gives me 155. 155 is the voltage of that 110 volt AC at its peak. So that value, 155, would be the peak value, and 155 would be the peak value. 110 would be the RMS value for the waveform coming out of the wall. that you would have at the in your room or at here at the university. So anytime you plug something into a wall socket, you can expect 110 volts AC, but that's RMS. So the actual value of the peak of that signal is 155. Each of the various waveforms has an RMS, an average, and a peak. So a square wave has the RMS of the peak value, the average of the peak value, and the triangular wave has the RMS of 0.577 times peak and the average at 0.5. We care about RMS values for power calculations, and that's why that's very important. When you're reading a meter, what are you reading? You're reading the RMS value of an AC signal. So anytime you set the meter to AC, you're reading the RMS value, and that's what you would then use for calculating power. So in general, we switch over when we talk about an RMS or a sine wave. We talk about it in terms of its RMS value. Unless labeled peak, usually you would assume that if I said 10 volts, that's RMS. That would be the RMS value. Okay. So if I said 10 volts with a squiggly, that means it's a 10 volt AC signal. And unless I define that the signal is something else. So that would be an AC sine wave signal of not peak value of 10, but of RMS value of 10. So it's going to be about 14.14 volts peak for that signal. So if I'm looking at it on the oscilloscope, at 10 volts, RMS would have a value of 14.14 for a AC sine wave. If you're looking at it on the oscilloscope, you would see that. Okay. So again, use your peak value or your RMS value rather as you would use the DC value and calculate your answers. And we'll pick back up in the next section, and we will talk about the problems at the end of this chapter. Take care. Okay, we're going to begin working on the problems at the end of chapter 6. So the first one, it says in the figure is 627a, find V when I is 1 second. So we're going to use the idea of a ratio, and we have 12 volts at 3 seconds, and they want to know what the voltage is at 1 second. So we're going to say times 1 second. We're going to cancel seconds, and it's going to equal 4 volts. And then at 2 seconds, so 12 volts in 3 seconds times 2 seconds, cancel seconds, and we have what? We have 2/3 of 12, or 8 volts. So that would be 6.1. In 6.2, we have a same type of problem, but in this one we are looking at milliseconds. So we have 6 volts in 2 milliseconds. So what would it be in 1 millisecond? Well, it's 6 divided by 2, or 3 volts. And at 10 milliseconds, 6 volts in 2 milliseconds times 10 milliseconds is equal to 60 divided by 2, or 30 volts. Okay, find the equation y equals mxb, or y equals v equals m times I, for 627a and 627b. So that would be y equals mx, or v, so for 6-3, v is equal to m times I. Or in this case, V equals M times T. So it's a ratio, and it's going to be, if you put in 12 equals M times 3, you get M equals 4. So our slope is 4 for that first one. For the second one, it's V, or 6 is equal to M times 2 milliseconds, or 2 times 10 to the minus third, okay? So M is equal to 6 divided by 2 times 10 to the minus third, or 3 times 10 to the third. So those are our equations. Okay, for 6.4, for the waveform of 627C, find the voltage at t equals 2, 4, 6, and 8 milliseconds. So 627C, just by observation, it's at 2 milliseconds, it's at 12 volts. At 4 milliseconds, it's equal to 0. At 6 milliseconds, it's equal to minus 12. And at 8 milliseconds, it's equal to 0 again, volts. All right, so number 5. For the waveform of 627D, find the voltage at t equals 1 second, 2 seconds, 9 seconds, and 9.5 seconds. So at 1 second, it is 3 volts per second, so it's at 3 volts. So it's 3 volts per second times 1 second is equal to 3 volts. At 2 seconds, it's equal to 6 volts. At 9 seconds, it's equal to 27 volts. And then it starts going down from 27 to 0, from 9 to 10. So at 9.5, there's half of 27.4, 13.5 volts. (6-6). In figure 627E, A closes at t equals 0 and B closes at 5 milliseconds. What is the current waveform through the first 2K resistor? So basically here, 6-6, we have this circuit at t equals 0. We have a circuit with we have a circuit with a 8K resistance. So before we switch A closed, we have a circuit with 12 volts and 8K. So that's our resistance. What is the current through the first 2K? So it basically is 1.5 milliamp up till when it's less than t equals 0. Okay. Then at t equals 0, A closes. Now we have 6K in parallel with 3K, or 2K, and we have 2K up above, so we have 12 volts divided by 4K, or 3 milliamps. T greater than 0, less than 5 milliseconds. And then at B closes, and now we have 6 in parallel with 3 in parallel with 2, so 6 and 3 is 2, and 2 and 2 is 1. So we now have 6 and 3 is 2, and 2 and 2 is 1. So we now have 3K, so it's 12 volts divided by 3K, or what? 4 milliamps. So it is between t greater than 5 milliseconds. Okay, so those are our answers, and that would be it would go 1.5, then 3, then 4. Now it says sketch the eye in the figure 628A. So this would be 6.7. So sketch I in the 1K of this circuit at the right. So now in 6.7 we have to Thevenize the circuit. So we basically say, okay, if I am going up at the rate of 5 volts per second, and I Thevenize it, I'm going up at the rate of 2.5 volts per second. So the V Thevenin would be exactly half. So at 1 second it would be 2.5 volts, 2 seconds it would be 5, etc., 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 because the voltage splits exactly. And what would be R Thevenin? Well, it's 6 in parallel with 6, or 3K. So we now have 3K. We have our variable supply, and then we have 1K out here. So at 1 second we have 2.5 volts, and we have 4K. So what would be the current at 1 second? .5 divided by 4 is equal to 0.625 milliamps. So we would have a graph of at 1 second, it would be 0.625 milliamps, and then at 2 seconds it would be double that, and 3, etc., etc., etc. So that would be the answer to 6-7. 6.8. Sketch V at node A in 628A. Sketch voltage at node A in 628A. Well, it would be the voltage would be we have 3K and 1K, and that 0.625 0.625 or excuse me, 2.5 volts, and we would say what would be the voltage at that. It would be 1 over 1 plus 3, or voltage divider, times 2.5, or 1/4 divided by 4 is 0.625 volts, which is exactly what we had before, which is 0.625 milliamps through 1K is 0.625 volts. It's exactly the same. So it would be at 1 volt, at 1 second it would be 0.625, at 2 seconds it would be double that. Okay, now 6.9. Sketch I and the 1K of 628B. So 628B is another Thevenin equivalent circuit, and we now look at it and say, okay, what would be the voltage across at the V Thevenin? What would be V Thevenin? Well, let's use the 24 volts, and it would be 6 over 6 plus 3, 24 times 6 over 6 plus 3, or it would be 2/3 of that would be 16, and that would be the voltage V Thevenin. So then we would use, that's our V Thevenin voltage. Then we would use the 2 plus the 2K, so it would be okay. Hang on a second. Gotta get over here and shut this thing down. Oh my goodness. Come on. Lost my mouse. I just shut it down.
I just need your key. I got myself.
Oh, okay. Okay, so use the 24 volts, and that gives me my V Thevenin. Now we also have an R Thevenin with that, which would be 2K, is 2K plus 6K in parallel with 3K, or 2K, so that's equal to 4K. So we have 16 volts, and we have 4K up here, and we have 1K, and they went into the I. So that's an easy circuit to do. It's 16 divided by 5, or 3.2 milliamps. And that is at the peak. So we go to the peak, and it's 3.2 milliamps, and come back down, and goes minus. So we would graph that, and it goes up to 3.2, down to 0, down to minus 3.2, and back. So that would be 3.2, minus 3.2, etc., etc. Okay? So that would give us the answer of sketch the I in the 1K, then sketch V across this 1K, which would be, again, 3.2 volts, and we'd be all set. So we can do that as well. Okay, now, that's B, and that would be 10 would be the sketched voltage, which would be 3.2 volts minus 3.2 volts, and you're all set. 11. Use the square waveform of figure 328C to find the current through the 2K resistor. So here we are, 611. And we're going to pick off the 12 volts. So we're going to use that as our reference. And then we're going to go through and we're going to do a Thevenin of this circuit. So we're going to Thevenize it. And the voltage 12. So if I use 12 volts, just like we did before, and I drew it like this, and I took out the 2K, so if you use the 12 right there, and I had 3 here and 6 here, and I had 6 here, and I had 3 here, so it's voltage at A is equal to 6 divided by 6 plus 3, or 6 over 6 plus 3 times 12, or 2/3 of 12, or 8. And V at B is equal to 3 over 6 plus 3 times 12, or 4. So VA minus VB is equal to 8 minus 4, or 4. Our resistance is 3K in parallel with 6K, plus another 3K parallel with 6K. And this is 2K, and this is 2K. Add them together, and we get 4K. Now we can reconstruct. We have 4 volts, we have 4K, and we have 2K. What do they ask for? They want the current. So they want the current through that resistor. So that resistor would be 4 divided by 6K, or 4 divided by 6K, or 0.67 milliamps. And then sketch the waveform at each position. So basically that would be, we would do that by saying, okay, find the voltage across the resistor. So basically we're going to, in this case, we're going to say it's 0.67 times 2, or 1.33. So we go up 1.33 down to minus 1.33. That would be our waveform. Okay, that's number 11. 612. Sketch the waveform at each position of 329A. So this one I'll just do for one, but this is a multi-position selector switch, so we have voltage across. So I'm just going to use it at the across the first position with across the 100. So it would be 7 times 100 over 100 plus 900 plus 9K. So it's 9,900 and 9,900 plus 100 or 10,000. So basically it's 100 over 10,000. We could write it this way: 9,900 plus 100, which is equal to 7 times 100 over 10,000. So we scratch out zeros, and it's 7 over 100, or 0.07. So 7 divided by 100, or 0.07 volts. At the next position, I'll just do the next position as well, it would be 100 plus 900, or 1,000, over 10,000, or 1/10, or 0.7. And the other one would be 7. Or the other one would be 7. The other one would be all of it. So it would be 0.07, 0.7, and then 7 volts. Okay. So that gives you the answer to 12. The next one, 613, the waveform of 629B. Okay, so they want to know the 10K, across the 10K. So here we are. We're now looking at a dependent source, and we've got a voltage of it's 1 millivolt, and we say, okay, now that through a 100 ohm resistor gives me what? What's the current? 1 millivolt times 100 is equal to divided by, gotta get this right, Ted. V equals IR. V divided by R is equal to I. And R is 100. So 1 millivolt, 0.001 divided by 100 is I. So that would equal, that's 1 times 10 to the minus third divided by 10 to the 2, or 1 times 10 to the minus 5. Okay, so now we multiply that by 10K, and that gives us, we multiply that by 50. So now we go through and we multiply that by 50. 50 times 10 to the minus fifth, and we multiply that, that's our I, and we multiply that by 10,000. Or 1 times 10 to the fourth. Okay, so now we've got a 50 times 10 to the minus fifth times 1 times 10 to the fourth, so we come up with 50 times 10 to the minus 1, or 5 volts. That's the answer to 629B. And it sketched the waveform, so that would be at the peak. It would be 5 volts, and then minus 5 volts, and then 5 volts. So this would be 5 volts. The one for C, 629C, is a sawtooth, and it is on top of a 10 volts DC source. Sketch the waveform and voltage forms across this 10K. So you basically would do this with superposition. So basically 614 uses superposition. So we would use the time varying source, which would be the 0 to 10, and that would give us 10 volts through 10K, or 1 milliamp. So it would be 1 milliamp, and then the other would be 10 volts. That would give us 1 milliamp. So our output would be 1 milliamp to 2 milliamps, back to 1 milliamp, back to 2 milliamps, back to 1 milliamp, back to 2 milliamps, like that, and that would just keep going. So this would be 1 milliamp, this would be 2 milliamps. And you can do that by observation if you want to, but basically, if you see that this one is contributing 10 volts and 10K, that's 1 milliamp. The other one is 10 volts and 10K, that's the other milliamp. So you got your DC supply right here. This is your DC side, and up here is your AC side, or your time varying side, and that's all you need to see. And that's the whole answer right there. 615. Use the waveforms of A, B, and C below to find the power dissipated in two resistors and the RMS value of current. Okay, so A, B, and C. So if you look at the circuits on page, let me go back and look. Let's go back to the RMS values of these. Okay, so for the sine wave, the RMS is 0.707 times peak. So the peak is 8 times 0.707, and then that would give me my voltage, and V divided by 15 would give me my I. So that would give me my voltage for that one. So that would be 8 times 0.707 equals 5.65. For the square wave, its RMS is equal to peak, so the square wave, it would be 8 times 1, or 8. For the triangular wave, the RMS is 0.707. So for the triangular wave, eight times 0.577 equals 4.616, and that gives me the ability to then go through and calculate the value of the power. So that power dissipated in the two resistors. So basically, if I have a 10K and an 8K, that would give me, or 25, that would give me 10K and 15K, give me 25K. So I have to find the voltage across each one. So in general, it would be like this. It would be 10, it'd be 5.65 for the sine wave times 10 over 25 would give me my voltage. And then square that over 10K would give me my power through the 10K for the sine wave. The 5.65 times 15 over 25, that squared over 15 will give me my P over my 15K for the sine wave. So this is the formula, and I'm going to let you do the rest of them. But basically, it's 5.65, 8, and 4.616, and then you find your power based on those variables. So that will give you the answers for that last question, 6.15, and you're all set. Take care. Have a good day.